We have, okay, let me just bring this here. We're gonna make a new folder, call it assignment 2. And at this time, I'm gonna copy, I think it's easier if I just copy all of this and put it here. And like I'm gonna just rename these things. Libraries are gonna be the same. We're gonna be working mainly with this Quant matrix library this time because we're gonna use transformations are gonna be implemented here. And okay, let me just drag and drop this here. Let's see. We got. Yes. Okay. Yeah, here we have the shaders. Let me. Here we have our shaders, and this example here is pretty much a red triangle, or like in this, it's a, yeah, if I do this, probably. This is our previous example. Let me open that before, let me just change this to assignment 2. Okay, and now let me open this guy. Okay, this should be assignment 2 as well. There you go. All right, let's start with the transformations. Let's try how does transformation work, right? So conceptually, let me try to annotate something here. I'll see if this is going to work. Let me see if this works. Okay, this is the other way around. Okay, so what we do, if we want to, if you want, let's talk about, for example, if I want to translate, wow, sorry, my handwriting is not the best, but if I want to translate, if I want to translate this triangle, let's say to the right, I have 3 vertices here, right? I have, let's call them V1, V1, V2, and V3. And these guys are actually defined in our code. Let's get them. Where is it? Right here. Okay. Let me change the color a little bit, maybe red. So we then, this is our V1. This is our V2. And this is our V3. Sorry. V1, V2, and V3. So when you want to translate these, or pretty much, let's say, move all these vertices to the right, or move the triangle to the right, essentially what you have to do is kind of apply one transformation or this translation to every one of these vertices. Okay, and we do that, and you'll probably have seen this in class, but just let me just quickly review this. We can do that by multiplying these vectors by a matrix. And for translation, right, we have a specific, we have 3 or a few more like special matrices that we normally learn in computer graphics. But for translation, normally you have a matrix T that looks like this, right? You have 0, or my bad, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And then here we have X, Y, Z, and 1. And this X, Y, Z here is the amount that you want to translate your vertices. So for example, if I want to move V1, V2, and V3 to the right by 1 unit, I could make the matrix, I could set X to be 1, Y to be 0, and then Z to be 0. In this case, if I multiply now T times, for example, V1, and T times V2, and T times V3, Let's call these guys V1 prime, V2 prime, and V3 prime. In this case, this resulting triangle here would be this triangle here translated by 1 unit, okay? And the same idea applies for rotation and scaling. Sorry about my handwriting, drawing on this tablet, and the computer is a bit laggy, so it gets really bad. But hopefully you can understand. So we can store transformations in matrices, and I'll let James discuss this idea, how and why this is a cool idea. But it's very important in computer graphics. It makes it much faster for us to do these transformations. And pretty much this comes from linear algebra concept. But this idea of having 4x4 matrices to represent transformations is very cool, because by having this 4x4 matrices and not a 3x3 matrix, what we do is we can multiply these matrices, for example, rotation and T and a scaling matrix, for example, to get a combination. We can compact all these transformations in one simple resulting matrix. So James will discuss this in class, but this is something that we have to remember for this assignment, is this idea of multiplying different transformations and combine them in a matrix M that pretty much performs all these three all together. And we'll be doing this in this assignment. We will be doing these multiplications ourselves. But thankfully, our library already implements or already has functions for us to create this specific matrix T, the R matrix, and the scaling matrix. So we don't have to worry about this in this assignment. We're going to reuse the library. One last comment is, if we are dealing with 4x4 matrix, and right now our vertices, they are actually only made up, they only have X and Y coordinates, right? Oh God. They only have X and Y coordinates, right? We can't multiply, in this case, let's represent the vertices as a column. Let's think about them as a column like vector. We cannot multiply T by V1, right? Because this is 4x4, this is 2x1. So we have to make this 4x1 to be able to multiply this matrix by this vector, okay? So what you're gonna do is, for 2D shapes, we're gonna just add a 0 here and a 1 on the last coordinate. And the 0 is because we don't need Z, and 1 here is because this is gonna be important for us to combine. If you wanna be able to combine these transformations by multiplying all of them together, we can show this later, but you're gonna have to keep this as a 1 and not 0. So, and that's it. And for the cube, this won't be 0. Some of the vertices will have 0, but some of them will have 1 or other values. So, but this will stay 1. So by doing this extension of the vector, now we can multiply T by V1, V2, and V3, and then do the transformations. Okay. Any questions about this theory before we get started? This should be just simple linear algebra. Okay, wait, let me see if I can actually properly see the chat. Okay, yeah, too many things to organize. All good. Okay, let me clean this up. And make sure I can type. Okay. Let's start by creating a matrix. Okay. First thing I want to do is create a matrix. And this is going to be, we're going to be using, let me show you like these functions here actually. We're going to be using functions from the Quant matrix library. So here, this library, as if you open it and start looking at it, you're gonna have this matrix 4 class here that you can create um, to do any operations with matrices. And pretty much it's going to be 4, but we only have, I think, matrix 4 and matrix 3, I guess, but we're going to be only mainly using matrix 4. And here we have, it's a kind of a different old style of making classes in JavaScript, but you can think of this as a class. And then you have some functions like set identity. You can set different values. You can concatenate a matrix. You can multiply a matrix by another matrix. You can do like multiply by a vector 4. You can, and here you can transpose. Anyway, there's a bunch of different functions for you already. Invert the matrix and so on. We will be using a lot of these functions today. Okay, so I do recommend you opening this file if you want to see how these things are implemented, and also like to have an idea of what you can use. And this is already included. So let's start by creating a matrix. And we're going to be creating a matrix here in our main memory now. So create a matrix. And this is, for example, lat m, or let's call this a translation matrix. Translation m, and this is a new matrix 4. So if I do this and print this, right, let's see what happens. I'm going to bring my console. Yeah, we see here the matrix 4, see on second print here. And if you open it inside, there is an attribute called elements. So matrix 4 is this class, and if you want to access the real elements of a matrix, you're going to have to print matrix translation m dot elements. So this is going to give you the actual elements of the matrix. As you can see right now, this is an identity matrix. And this is actually stored as an array, but you can interpret this as a matrix as follows. You can think of this 0, 1, 2, 3 elements as the first row, and then these next 4 elements are the next second row, and third row, and fourth row. So it's stored as an array, but it's actually the class handles it as a matrix for you. You don't have to worry about this. So cool. So what I want to do is I want to send this matrix to our shader, right? So I want to do that using an uniform. Normally, transformation matrices are sent to the shader as uniforms. And that's because you want the same matrix, let's say a translation matrix. If you want to translate all the vertices by 1 unit, you're going to have to apply the same matrix to all the vertices. So normally transformation matrices, because of that reason, normally they are uniform variables because they are the same matrix for every vertex. So let me show you how this is done. We're going to say uniform. And here we have this type called mat4, which is for matrix 4. And I'm going to call this u underscore, let's call this translation matrix, okay? And now we know this is very similar to what we have done with the caller. Remember, we had the uniform to send the caller. Now we have a matrix, but it's still uniform, so the concept is the same. We now need to send this uniform from the main memory to the GPU. And let's do that again. So we know how to do that because we did that with caller. So let me organize this and put this right after the caller then. We're gonna have to retrieve the uniform u. Let me copy that, sorry. U translation matrix, okay? U translation matrix from the shader. And this is the same. You can say U translation matrix equals to gl.get uniform location, gl.program, and then the string with the name of the shader of the variable. Again, U translation matrix. Okay, good. Now we have to do the same we did before, which is set the U translation matrix uniform. Now we are calling that function gl dot uniform. Here we're gonna have a different how do you call it? Function to send it, and this is uniform matrix for. Let's use FV. I told you this before, but for each type of uniform, you have an associated function in WebGL. So you're gonna have, because it's a matrix 4 and it has floats in it, and here the V is because we are sending it as kind of a vector or one array, and we are doing this because our matrix in the library, it's already represented as this float 32 array. So this is going to be very helpful. Here, what we're going to do is now we want to change the translation matrix. So this is the first argument. We're going to set the normalization. We're going to set this to false. This is to, if I'm not wrong, this is actually to invert or no, transpose. This is to, if you want to transpose the matrix. We don't want to transpose the matrix. And here we want the data or the actual matrix, right? And here we need to pass our variable translation M, which is our actual matrix, dot elements. So with this line, we are updating the uniform U underscore translation matrix with the values from our matrix in memory, which is defined here as the identity matrix. Okay. So right now, if we reload this code, I'm going to do this, refresh the page just to see if we introduce any bugs or any errors. Refresh the page. It seems everything is working fine. But we haven't used this in the shader yet. We didn't do anything with this matrix, right? So let's do that. Let's multiply. Remember from, I showed the theory before, if you want to apply this transformation, you can pretty much multiply this matrix by the vector. And I see this is a vector 4. It has X and Y coordinates, 0 equals to Z, and 1 as the final W coordinate. This is exactly what I showed before in my notes. So let's see what happens if you do this. Okay, nothing happens, but also we don't get any errors. Remember that this matrix, as it is now, is just the identity matrix. So if you multiply the identity matrix by any vector, you get the resulting same vector as output. So we need to do something with this matrix to see some visual change. So to do that, we're going to use a function from the library, and we're going to change our matrix now. Let's get our matrix. Where is it? It's well, here, right? So we're going to call here on this variable set rotate, or let's call set translate first. Set translate. This is a translation matrix. Note that it's a translation matrix because I'm calling it a translation matrix. But when I call this line here, now because at line 90 is just the identity. Now I'm going to make that an actual translation matrix. Let me show you how this function looks in the library. So if I search for this, you have this function here. And as you see here, see like the first column is 1000, the second column is 0100, third one is 0010, and then the fourth is XYZ1. This is exactly what I showed before, right? In my theory, in my notes. But here you have the actual function implementing that same concept. I want to show this because I want to show that the arguments we need to pass. So we need to pass 3 arguments, x, y, and z, which is the amount in units that we want to translate our vertices by. So here we're going to have to say like 1, 0, 0. So we should expect now this triangle to be shifted to the right by 1 unit. Okay. And that's it for the translation part, right? Let's see what happens. There you go. We got our triangle shifted. And we can do 0.5 here. So you see a little bit less, okay? So this is it for transformations. We are for translations, at least. I want to show you some different ones so you have reference and what you can do to multiply all of them.